first two ways that we solve things were substitution and elimination. That was review from last year, hopefully anyway. Today we're going to solve graphically. Some of these slides are pretty irrelevant because we've already gone over the topic because I reversed the order of the way we do this unit. So this first slide is reminding you that when you get solutions in this unit, you're getting coordinates, you're getting actual points. And that's what matters in this whole unit is you don't solve x equals something. You get an actual point. You'll have a point 1, 2, and that'll be your answer. So you need to remember to answer things in that format. We've talked about that plenty already. Here's a couple of pictures. We already drew some of these for you. When do you have solutions to system of equations? So if you're given two lines, where do you get a quote-unquote solution? It's where they cross. It's anywhere that they touch each other. So in this first one, the two don't touch each other at all. So are there any solutions? No. So this would have no solution. It would have no solution, no intersection, no coordinate that both share. System B, how many solutions would you have? You would have an infinite number of solutions. They're right on top of each other. And that will happen every once in a while. If you have two solutions that are perfectly on top of each other, you have infinite solutions. And the last one, time.
What does that mean?
It means, so remember a solution is a coordinate, right? This means there's an infinite number of coordinates you could find where these two things are touching each other. And that makes sense, because if they went forever, they would still always be on top of each other. Right, exactly, yeah. System C, how many equations? How many solutions do we have? 1. Where is it? It's got 1, 2. Again, this is a review. This is literally a slide straight out of grade 10. That should all be familiar, plus we reviewed it on Friday. That was when we did linear. Now we do systems of equations with quadratics. And we did a little bit of practice and we drew some of these things out. But here's some nice drawings, unlike mine on Friday, showing you how many solutions there are. How many solutions would you have right here? Why 0? Because they would never cross each other. Perfect. Here. 1 solution. So it touches right here, and then it keeps going past. So you got a curve, it comes up, it gets really close, it just nicks it, and then it keeps on going.
It kind of looks like it goes like along with it.
Yeah, it almost looks like it's like running alongside of it, but it's actually just touching it and then leaving. It's called a tangent line. You don't need to know that, but that's what it's called. A tangent line is something that touches once and then keeps on going. Yeah, that would be your tangent point, where it came, it touched, and it kept going. In university, that is all you're going to work with. This is calculus. That's all you do in calculus, is you find tangent points. How many solutions for this last one? 2. You got 1 here, and you got 1 here. You could have more than 2 solutions if you had a quadratic and a quadratic, because then they could be right on top of each other. Right? But if you have a linear and a quadratic, the most you can have is 2. Yeah. If you had a linear and a quadratic, or a quadratic and a quadratic. Yeah. You'll never get more than 2 if it's linear and quadratic. Time.
Does the quadratic just mean it's square?
Yeah, that's all it means. Josh.
If there was 2 parabolas, it was up, it's not still going.
I think we look at that in the next slide. So we'll answer when we get there. I'm pretty sure. If we don't, then I'll answer that. Again, on the bottom, a nice little note. This is how you put in your answers, and it tells you how many possible solutions there could be for a linear quadratic system of equations. Here's quadratic, and this is what we were working with on Friday. We were solving them by hand, using substitution and using elimination. Graphically, this is what they would look like, where you have one quadratic graph and the other quadratic graph. Situation 1, how many solutions would we have?
0.
0. Why would we have 0 solutions? Because they would never touch each other. Perfect. This one, how many solutions would we have? 1. Right here. 1 solution. Down here, how many solutions would we have? 2. They've crossed here and here. And the last case you get for quadratic is this. These look like 2 very different quadratics. They're not. They're in different forms. One's standard form, one's general form, but it's actually the same quadratic. So how many solutions would you have? Infinite. You do that like this. Yes.
So, if they just give you this equation, you can just put it into the calculator and look at it.
Exactly. So if it asks how many solutions there are, in your calculator, you can just look at it. What I'm going to show you is how to find the exact points in your calculator.
Well, interesting.
Yeah, it's easy. Okay, Josh's situation, which didn't come up. I thought it was going to be that. So Josh's situation was you've got a graph. They're the exact same graph, just one's translated up, right? So we'll say this is graph 1. And graph 2 is the exact same graph, just 2 units up. Would they ever touch? No, they would never touch, because they're always going up at the same rate. So how many solutions would there be? 0. Yes. Well, that's a good situation. That's a good question. Yeah.
Will there ever be like a part where they're not exactly on top of each other, but they like...
So like put it right close like that, but not actually touch? Probably not.
No,
Probably
like it
not.
doesn't touch at the bottom, but because like one of it's gotten skinny or something, and they touch it.
Oh yes, that is possible. So another situation here. Beta's got a good question. Your first graph is like this, and your second graph is translated up a little bit, but it's a little bit wider. So it's going to come through like this. And that is possible, and you'd have right there and right there. So the only way that you would get 2 graphs that are either perfectly on each other is if they're the exact same graph. And the only way you would get one that's the exact same but just above it and not touching is if you had this form and they had different Q values, but everything else was the same.
Okay, I have a question.
Just London. Another good question. You'll never get 3 or 4 or 5. You'll never get anything above 2 unless it's infinite. So you think about it, there's no way you could draw parabolas like that and get more than 1. That means you must have another curve somewhere in there. Quadratics always have just one curve. And that's what makes it possible. Stop, put it away, whatever it is. Julie.
This page, the one that we just did with the straight line. Yeah, the first one. Wouldn't the parabola eventually touch?
That's a good question. So she's saying, oh, here, would it not eventually touch? Once you get up here, you're actually going up more than you're going wide. So the further you get away from center, the further up you go than you go wide. So it would never touch. It would never touch.
Okay. And the blue line just goes.
And the blue line's always going at a straight distance, 1 for 1 on the way out.
What if you graph like sine, cosine, or tangent? It's like when you graph sine of x, it's like snakes along the x.
Yeah, that's going to be probably a solid 3 months of Math 30-1. And Doug.
It touches on the third graph and on the bottom, right there. And there's on the other slide, the second one, the third graph.
Yeah.
It touches in the middle too.
So the graph is like this, and like this. So you want to know just where the graphs touch the other graph.
Oh, but that one is.
Yeah, just here and here. On the other one, it happened to be that they also landed on the X, on the origin, but the big thing was that they landed on each other. Yeah. That.
The two quadratic equations, graphing. How is it that it's not worse?
I see what you're saying. Okay. You could try it. You could legitimately try it. Like, you could draw any situation you want. You could draw any true parabola, whatever you want them to look like. And you'll never get them to touch more than twice, unless it's infinite. And the reason you'll get it never to touch more than twice is it only ever changes direction once. So every time something changes direction, it adds an opportunity for it to cross again. If that makes sense. If you're crossing a road, you only touch each side of the sidewalk for every time you cross the road, right? So if you only cross once, you'll only ever touch 2 times maximum. Josh,
So
like this.
yeah.
Okay, so there's lots of different types of equations. In this class, the largest exponent we ever deal with, x squared. And there's a reason for that, because that's what gives us these parabolas. If you have more than one term, or what I can't tell you the word we use after dash one. Yeah.
Exponent.
I think we call it term in math 3-1. There's bends and there's terms when you get to math 3-1. I just want to use the right word right now. I don't know what that is. Pretty sure it's term. If you have more than one little bend right there or turn, that means you don't have a quadratic, which means you probably did something wrong, because we only ever deal with quadratics. Equations that look like this could be lots of things. It could be a sine graph, or it could be a tan graph, or a cosine graph, or it could be an x cubed graph, or an x fourth graph, or so on and so forth. And that's all stuff you'll do in math 3-1.
Are we going to get into like sine squared and stuff like that?
Not until next year. No. And we'll never graph sine squared and stuff. We only ever graph sine, cos, and a little bit of tangent, but tangent graphs really suck too. Josh.
What's like the highest exponent?
Infinite. You go forever.
X the power.
You can go forever. You might not be able to see it on your graph. It might be difficult, but they will go forever.
What about X? It's like it
X.
goes, yeah, it goes
Negative
into like
what?
different like
Okay. You won't see that in this class either, but x negative 1 is just 1 over x, right? That's our law. You'll never deal with that either in this class. You'll never have an x on the bottom of a fraction. Not going to happen. That's a good question. I don't even think you'll graph that next year. You might in college, depending on the courses you take.
so it like goes along the X and then it curves to
Actually,
the Y. And then
No, you will do this in math 3-1. Yeah, we just call them inverse graphs. Yeah, where it makes asymptotes. It's something you won't need to learn until next year. And it's not fun. Okay, is everybody solid on the quadratic idea and graphing? Okay, let's try them. So, my suggestion to you guys, star this slide. Star it. It's the one you're going to come back to anytime you have trouble graphing something, because it's your instructions on how to graph. If you ever can't graph something, go back to this slide. Don't ask me how to do it until you've at least tried on your own. What you're going to do is you're going to graph them. Same way we've graphed everything. You go y equals, you put in one equation as y1, you put in the other one as y2. You hit the graph button. You then will use second, trace, intersect. Those are the buttons in the sequence you need to hit them in. Alright.
Solving the graph. Solving quadratic.
Nope, exact same. So this will solve, and the reason why I say this is so important for next year is you can use the same strategy for next year when you have to solve equations, which you will have to do. And they try to find ways to make you do it algebraically, but it's hard to try to make someone do something algebraically. So what we do is we teach you that you could just graph two equations and you're good. Yeah, the diploma is really good at that. Really good. This year? Yeah, we're also going to do that because we're trying to get you ready for that next year. That's why I showed you as substitution and elimination first, because it's more valuable for where your head is. Soccer.
I'll ask you.
Okay. Okay, let's do this one together. So, what is the solution for the system of equations? You have these. You have three options now. You can use substitution, you can use elimination, or you can graph it. You can look at the beautiful graph here, but it probably won't give you a nice beautiful graph. So what we're going to do is we're going to use graphing. The first thing you need to do if you want to graph something, hit y equals. What do you notice? Everything's in y equals. So we need to get these two equations to be y equals equations. So the first one, we're going to subtract 5x from both sides. And you get y is equal to 2 minus 5x. That's your first one. Your second one, you're going to add y to both sides, subtract 4 from both sides. So plus y, minus 4, minus 4. And you'll get y is equal to x minus 4. Put the first one in as y1. Put the second one in as y2. See if you can get off your phone, please. Try it. This is how you're going to figure out if you can do this stuff or not. Then you're going to set your window to be something that would make sense. If you look at my window right here, this is the graph you should get, so use the same window as me. Maximum 5 or 4. Yeah, standard graph works too, 10 by 10. Hi.
Counting to 5 instead of 5 on the other side.
So you want to move the x over and then divide out of 1? As long as you change all the symbols on the other side too, yes. Tanner. Okay, we're going to do that. Yeah, we'll do it together. Soccer, it's a problem we're all going to have.
What if for like you put a value in for x, like you have like because you're storing a value for x, and
That's why I don't want you storing values for x.
okay.
Yeah. Don't put a value in for x. You want an equation. You don't want a straight line. Like, if you put a value in for x, you're going to get a straight horizontal line somewhere. We don't want that. So make sure if you store anything as x, to delete it.
How do you do that?
Yeah.
X is 0.
No, because then you're storing x as 0. You need to, I just reset the calculator is what I do.
Isn't that what they do before you go into a chest and reset the calculator? Why don't we do that?
Because if you're good with your calculator, you can write notes in your calculator. Yeah. Don't sweat. It's not worth it, and it's a lot of work. It's worth it when you get to like higher level math. Not wait for this. Don't actually, don't download games onto your calculator. Like legitimately, because you are. So, hey, I'm being serious because you can download games, and eventually you're going to figure that out, and you're going to try it. And people have put viruses to the games on the calculators, and once your calculator gets a virus, it can't be taken off. So that's $120 down the drain. Then they disable your calculator. And I don't know why people. It's just a virus. Well, you downloaded it, like. I don't know. People sucks too. Josh. Okay. Everybody your calculator? You're going to go. Yeah, you didn't get a choice. Everybody get to this point. Put your hand up if you can't get those two graphs. We should all be there now. Okay, you're going to go second trace. There should be a word that says intersect. That's what you want, because you want the intersection of these two things. And that's how you get your answer, is finding the intersection. So you're going to go second trace, intersect. Yeah, just give 1 second. On the bottom, it now says first curve, right? There's no curves. But your calculator doesn't know that, because it's just a calculator. All it's asking you is, are you on the first line? It's the same thing.
Well, how do you know which one's first
Yeah.
and second?
Doesn't matter. So if your calculator's already on a line, that can be your first line. It doesn't make a difference. So hit enter.
It's already.
And then your cursor should move to the other line.
Yeah.
Hit enter again.
Does it matter like which side?
Doesn't matter which side. Nope, you're good. This one's a lot easier than anything else. And then it should tell you it's at 1, -3, right here. So your answer would be 1, -3. Pardon? That's the solution to this system of equations. And you can see how valuable that'll be when we get into quadratics and stuff like that.
So instead of doing all the
Yeah. As long as your questions are just like this, and they're just asking for an answer, then yes. But again, substitution and elimination will come back when they start using variables instead of numbers. So it will come back. Yeah, it's for the tests. So you need to know all 3 methods, right? We're not one-trick ponies in this class. Where this becomes extremely useful
Yeah.
will be on word problems and application questions. So that's our next lesson tomorrow. Because we're going to get some crazy equations. And this is so much quicker than having to figure it all out through elimination and substitution.
So on substitution equations, you can do elimination, right?
Yeah, you can do any method you want, and it'll always work. Some might just be harder than others. So remember I told you if you have coefficients that won't match up, like if you have like 2x plus 3y equals 6, and then 5x plus 7y equals 10, it's usually easier to use elimination, because your substitution is going to have such weird fractions in it.
Just do elimination.
Yeah, it depends. Yeah,
Because then you don't have to complete the square.
I like elimination. Yeah, Julie.
So what if you were using parabola and how would you use the intersect?
That's a very good question. I think that's our next question. Yeah, that is exactly our next question. So, we're going to do the first 2 together. You're going to do the second 2 on your own. So, in your y equals, graph both these things. It's already in y equals format, so that's perfect. And then just graph it. Get a window where you can see all the potential intersections.
But you know what I mean? Like I draw it on a sheet.
Yeah, draw an accurate graph on your sheet if possible. Yeah, that's fair. Just give me one. No, if there's 2 intersections, which there is, make sure you can see them both. That's important. You should be able to tell right away how many intersections there's going to be. Make sure you make a, like once you put it in your window, you should be able to be like, oh yeah, that's not going to touch at all, or oh, it must touch twice. I just can't see the second point. Love it.
So, I still equations.
Or we just
Yeah, it's the same thing. Same my button. Okay. Now it does matter where we pick things. So, is everybody at this point where they see this graph? Yeah, come on, give it a second. If you're at this point, you have this graph on your graphing calculator. There's now 2 intersections that you need to find. Our last one only had 1 intersection that you need to find, so it didn't matter where you chose. go second trace on your first curve. If you're on, most of you are probably on your quadratic, right? Your little cursor, because you probably put that in first. Your cursor just goes to whatever y1 is. That's how it decides which one to start on. If you want to find this point here, I'm going to put it in red. This is our first point we're going to look for. You need to move your cursor close to that point. You don't have to be dead on it, but you have to be close. Doesn't matter what side, just close. Josh. Yeah. And then hit enter. And then your cursor's going to switch lines. Again, get close to this point. It doesn't have to be dead on, just close. And then hit enter, and what point does it tell you?
X is 1.56, y is equal to negative 2.8.
Is that what everybody got? No?
I got 1.5.
Yeah, x definitely has to be negative. So
Sorry, what?
Yeah, see,
x is negative,
2.5.
y is...
I don't know.
Okay.
Do I go on 1.56 and negative 2.86?
So, Jacob and Bailey and anybody else who got 1.56 and something else, look at your graph and your cursor's probably up here on this other one.
Yeah,
Yeah, so you found the other intersection. Your cursor's not on the other intersection?
I don't even think the cursor's on.
Oh, it's not on it. Right. Yeah. If it doesn't say on top anymore,
The other one is negative.
the only reason that might happen is you're not close enough to the point you actually want to find. You just have to get closer to that.
Oh, I lied.
If you press up or down.
oh, so that just finds that one.
Just find one point, then find the other
So
point.
yeah, I went
Beta. Sorry, other beta. Okay, go ahead. Are you comfortable to try to do the next tree on your own?
Yeah.
Write the next tree on your own. Write down the answer. So, for the second graph, this one up here. This one up here. What's your answer?
That one?
Yeah.
I got 2 and 1.
2 comma what?
Yeah, I put my.
I got point.
Okay, so for what you get?
I got 0.39 and 0.2.
Yeah, we got 0.46. Actually, we round up to
I was so
Okay. Put your hand up if you didn't get that answer. Okay, Maddie, what'd you get?
I got the same thing. I got 2 answers. Yeah.
Okay.
I got 2 as well.
Okay, then that's a problem. So, hands all down. Put your hand up if you have 2 solutions. Okay, those are both correct answers. So you need to tell me both those answers, not just one. They're both right. You need to find both solutions. Ty, is this one of your solutions?
Yeah, that was my point.
I didn't get that.
Okay, hand up if you didn't get those at all. Alright.
Still wrong. Still wrong.
Okay, end on. What's your first solution?
First one is 463, comma 5713.
463?
Yeah.
4 decimal 63?
I think there might be decimal in there.
I got 0.46.
I think it's 0.4.
I got 0.46.
Yeah, that's one.
Oh,
And negative 0.86 and negative 0.49.
Okay,
Yeah,
There you go, that's negative 0.86
Yeah,
and negative 0.49.
that's right.
Negative
I
point.
didn't touch twice, so I just did one.
That's what I got.
Okay.
But I rounded up to 7.
Calculator takes so long to think.
Both those answers need to be there to be right. The grounding doesn't matter on the... Oh, it does. It says nearest tenth, so it really should have been rounded to the nearest tenth, not the nearest hundredth. Not a big deal, if you weren't really sweating about that. But make sure you're doing that properly in the future.
Oh, that's
Make sure you check where your decimal points are. It's also important. You need to be able to tell how many solutions there's going to be. So if you're looking at your window and you've only shown that much of a graph, because that's all your window is showing, there's obviously going to be a second solution somewhere over here. You need to adjust your window to get that second solution. You guys have to start using that kind of intuitive thinking to know where solutions are going to be and what kind of window makes sense. The other thing you need to do, especially when these graphs get close to each other, and it's going to happen, where the 2 points are very close to each other on, say, the x-axis. They're just a little like this. You got one like this, and you got one like this, and it just crosses, and then it just crosses again. You have to be zoomed in enough on your calculator to show you that. Otherwise, it's going to look like it just touches once if you're really zoomed out. That's another thing you need to be very careful of. You got to start using your own thinking power to be able to figure these things out. Zoom fit isn't the greatest anymore. Now you got to start thinking what actual window would make sense. What do you guys get for a solution for this one? No solution. What did you get for this fourth one? First solution, Jacob.
Negative 0.14 and 3.54.
And if you did just 0.5
And
and dog.
No, like, I'm almost positive I entered it all in right, but it doesn't touch it on my graph.
And this one? Yeah, come on.
Yeah.
I got 5.10.
And what?
10.95.
9.
5.
Okay. Do we agree with those two solutions? Hands up if you got those two solutions. Not enough hands up. Well, don't lie to me. I just need to know if you're actually getting these or not. Okay, we'll take a look at that. The last one. So, we're going to graph these two. The first one should be somewhere down here, and it should look something like this. Graph on your own. The next one should look something like graph it in your own calculator. Make sure I'm right. I don't have a calculator.
Yeah, that's close. Bit lower. It doesn't really matter.
You can get this on your computer.
Okay.
You can get like this stuff there on your computer.
Yeah,
Yep, you just
close.
I do. It's really, really crappy.
yeah,
It usually crashes my computer, and then it's. Yeah, Miss Tucker, she's going to give me the same thing.
also like paste and something like that.
No, it's a free download somewhere.
So you can get the thing on your computer for free, but you have to pay $100 to buy it out.
Yeah, that's how it is.
That's silly.
Does everybody have that on their calculator? Okay. The coordinates of our intersection should be pretty easy to get. What's this first coordinate over here? -2 and positive 2. What's this coordinate over here?
What was that? Wait,
That's my drawing's off.
Yeah.
Remember, I just was sketching it for fun. Okay. That's easy. And like I said, we're not really going to test much of can you just do easy stuff. It's going to be application questions and stuff like that. Problem solving. That's what this unit's going to be about. So the question is, how could you transform one of the graphs so that the graphs do not intersect? Emily. Make the 2x squared so it's 2x squared plus 5. What kind of transformation would that do? You're dead on right. Keep on explaining. Yeah. Yeah. Your C value, it chooses where the y-intercept is. So if you change this first one to have a y-intercept of positive 5, this graph right here, this graph would go from having an intersect of -6, and it would move up to have an intersect of plus 5. So, if you chose any number that was above plus 4, you would have no solutions. So if you did 4.000001, no solutions.
Change the second one over.
So the other question, leave that where it was. That's only one transformation. The other transformation you could do is you could take this one and move it lower. So that means if you change the C value to be less than -6, so -6.00001, no solutions. Remember, your C value controls your y-intercept. It moves it straight up and straight down. That's a vertical translation. Nope. You can do anything. Yeah.
Like, instead of saying like transfer y plus 5, but you said transfer y plus 50.
That'll be fine. Yeah.
That's okay.
Yeah.
So this won't be like a multiple choice question.
It could be. It could be which of the following transformations would make this so there's no solutions. And it could give you like a translation of +1. That wouldn't work. Translation of +10.
Yeah.
Oh, that would work. And then you can move it.
Move to the left by 2.
It's another good question. You could also move it off to the left. Or off to the right.
How about to the left?
You could also flip it and then give it the same stretch. These are all different transformations. So now you flipped it, you made it negative, and then move it up with inside of it. That would also work.
But then be like the same.
It doesn't have to be the same if the one on the outside is getting wider and the one on the inside is getting skinny. Otherwise, you're right, that would be the same. Anyway, yeah. Boys, control yourselves just a wee bit. A lot more than they are now. How are we feeling with this stuff? Any questions? I'm telling you, this is a useful skill for next year. They'll review it a little bit. Okay, you've got 20 minutes of practice book at a time.